In this video, I'll be discussing nucleophilic substitution reactions. So nucleophilic substitution reactions are going to be a special kind of Lewis acid-base reaction where you have some Lewis base called the nucleophile which wants to bond to the Lewis acid called the electrophile. But with nucleophilic substitution, the Lewis base is going to want to replace some group that's already bonded to the electrophile. And this group is called the leaving group. And the leaving group is going to be bonded to a carbon, which I've circled in red here, and this is called the electrophilic carbon. And essentially, the nucleophile wants to replace the leaving group. It wants to kick the leaving group off and take its place. So in this reaction, the F- wants to replace the Cl. So you see over here the products, the F wants to replace the Cl and kick it off. And that's all happening to this carbon I'm circling in red, the electrophilic carbon. And it's all well and good to predict the products of these reactions, because essentially you just replace the leaving group, whatever's bonded to your electrophilic carbon, with the nucleophile. You just kind of swap them out. The real question is, would this reaction actually move forward? And that's when we have to get into a little more specifics on strength, and particularly base strength. And we have to compare the bases here to see if this reaction would actually move forward. So with this reaction, what we're really comparing is the strength of the bases. Because for a nucleophilic substitution to actually take place, for the nucleophile to replace the leaving group, the nucleophile has to be stronger than the leaving group. So the question is this: in this reaction, which is stronger, Cl- or F-? Which is the stronger base? Well, remember, F and Cl are in the same column of the periodic table. What matters when you're in the column is size. So which of these is bigger, Cl or F? It would be Cl. Cl has a larger atomic radius. Therefore, Cl- is weaker than F-. So because Cl is weaker than F as a base, F is the stronger base, F is going to replace Cl, and this reaction would move forward. And it's moving forward, like I said, F- is a stronger base than Cl, therefore it's going to replace the Cl. Now, sometimes you might actually have to draw out this reaction, how it takes place. And you use this notation called arrow notation to show the substitution, and you have to draw what's called a transition state, or a transition intermediate, to actually show that the substitution is taking place. So remember, F- is going to have all these lone pairs around it. And so what's going to happen is, one of these lone pairs is going to be attracted to the electrophilic carbon. And remember, the electrophilic carbon is going to be the carbon that the leaving group is bonded to. So this right here is the carbon that the leaving group is bonded to. And what this is going to produce is what's called a transition state, or also you can see it called a transition intermediate. So here would be your transition state. And if you see this little symbol up here that looks kind of like a power pole with these two lines going through it, this is just the symbol that means transition state. And you always want to put your transition state in brackets. And you want to draw dotted lines to your two groups, to your leaving group and to your nucleophile. And what this is showing is, for a very brief moment of time, both of these groups are going to be drawn towards that carbon. So this is the process of the F bonding and the Cl breaking off. So for a very brief moment of time, this is going to be what this molecule looks like before the F fully bonds and the Cl fully breaks off. But the Cl will break off And the electrons from that bond are going to go onto the Cl. And so eventually, when the Cl breaks off, the F will stay bonded, and the F will end up replacing the Cl on this carbon. And this will give you your products of that reaction. So let's look at another example of one of these nucleophilic substitutions. Okay, so here we have this molecule here and I minus. And the question is, predict the products of this reaction. So we're not worried at this point whether this actually moves forward or not. We simply want to predict the nucleophilic substitution reaction in this case. So simple enough to predict the products, you just swap out the nucleophile in the leaving group. So I would become the new bonded group, and OH minus would be kicked off. So the leaving group would leave and the nucleophile would take its place. The real question is, would this reaction move forward? And for that we're going to need to compare OH and I. So ultimately we're going to compare OH minus and I minus to see which of these is stronger and which is weaker. Now there's a couple different ways you can think about this. You can think of it in terms of stability. You know, which one do you think is more stable, oxygen or iodine? Well, iodide is much more stable just simply because it has a lot more electrons. It's bigger, it has more electrons, therefore it is going to be more stable, making it weaker. That would mean OH minus is the stronger base. That's one way to think about it. Another way you could think about this is to use some of your Bronsted-Lowry skills to compare them for strength. And to do that, what you could do is turn them into acids. Right? If you turn each of them into conjugate acids, you just add one hydrogen to them. So OH minus would become H2O, and I minus would become HI. Now, which of these is a stronger acid? Is H2O or HI a strong acid? Well, we know HI is a very strong acid. HI is a very, very strong acid. Water is a very weak acid in comparison. So remember what we said when we talked about Bronsted-Lowry acids and bases. If your acid is really strong, that makes your base really weak. So if HI is a really strong acid, that means that I minus, which is the conjugate base, is weak. So this would be very weak. H2O is a weak acid, therefore OH minus, which is the conjugate base, is strong. So using that logic, we have determined that OH minus is the stronger base, which means that I minus would not be able to replace the OH. So this reaction would not move forward because OH minus is stronger than I minus. It will stay just like it is. This reaction would not move forward. So that's sort of how you have to compare them based on strength. If this way is confusing to you, turning them into acids and then comparing, you could use stability and other ways to determine this. But I've always personally really liked turning them into acids and comparing them that way. Whatever works for you, really. But at the end of the day, this reaction would not move forward. So let's look at one more example here. And this is a really interesting example, I think. So here we've got this compound and we've got a methyl group, CH3-. And to predict the products, simple enough, you just swap out the leaving group and the nucleophile. So that's our product prediction. You just swap out the Br for the CH3. And so the real question, of course, is does this move forward or not? So for that we have to compare Br and CH3. Which of these is the stronger base? So if we go through the process of turning them into conjugate acids by adding an H+, CH3 minus becomes CH4, and Br minus becomes HBr. Now, which of these two is a stronger acid? Definitely the HBr. HBr is much, much stronger than CH4. So remember, that's going to mean the opposite in our base. So if we have a really strong acid, that means our base is going to be weak. And if we have a weak acid, that means our base is going to be strong. So therefore, CH3 minus is a stronger base than Br minus. So because the nucleophile is stronger than the leaving group, yes, this reaction would move forward. In general, CH3 minus is a really good nucleophile. So just to break that down, I guess one more time real quick. CH3 minus is a stronger base than Br minus. So CH3 is the nucleophile. If the nucleophile is stronger than the leaving group, the reaction will move forward. And in this case, the reaction does move forward. So I guess to wrap it up, here's a quick checklist. These are the kind of combinations you want to see. You want to see a good nucleophile paired up with a good leaving group. Because if the nucleophile is stronger than the leaving group, then of course your reaction will move forward. Here are some good nucleophiles to look for: CH3 minus, OH minus, F minus, SH minus. Some good leaving groups to look for: I minus, Br minus, and OSO2CH3 minus. Although, remember, it's always relative, so always make sure you check and compare your two bases to see which one is stronger. Because sometimes you'll get a combination of a leaving group and a nucleophile where it won't be as straightforward which one is good and which one is bad, basically. Which one is a better nucleophile, which one's a better leaving group. But just as a quick rundown, these are some of the common ones you'll see that are good. So these are good leaving groups. They leave very well. They're very easy to replace. And these are good nucleophiles that are very easy to replace the leaving group with. So these react very readily, these leave very readily. And these are the kind of combinations you're looking for. But always make sure you just look at your reaction thoroughly and compare the two bases that you have in your reaction. That's ultimately what's going to determine whether the reaction moves forward or not. A strong nucleophile will replace a weak leaving group. The other way around, there'll be no reaction. A weak nucleophile isn't going to replace a strong leaving group. So that's the basics of nucleophilic substitution that you'll need for Gen Chem.